Welcome to this explainer. Today we're taking a ground-up journey from the absolute basic units of physics, right down to the messy, complicated reality of imperfect physical measurements. So let's dive right in and decode the bedrock tools that scientists use to understand, well, the entire universe.
Okay, let's lay out the roadmap for today. First, we'll hit the foundation of physics, then move on to decoding dimensional analysis. After that, it's scalars versus vectors, followed by multiplying vector quantities, and we'll wrap it all up with the reality of measurement.
All right, Section 1, the foundation of physics, starting with the basics.
Before we can analyze, say, planetary orbits or massive energy systems, we really have to start at the bottom. And at the absolute heart of it all is the physical quality. This is basically any measurable property of a physical system that you can express with two things, a numerical value, which we call the magnitude, and a unit. Literally every single physical phenomenon you can think of relies on these two interconnected parts. You absolutely cannot have one without the other.
In fact, to quote our source material directly here, without units, numerical values have little physical meaning. Just think about that for a second. If I tell you the answer to a physics problem is 5, well, that means absolutely nothing on its own. Are we talking about 5 meters, 5 seconds, 5 kilograms? The unit is exactly what anchors that completely abstract number into physical reality.
Now, look at these 7 pillars we're showing here. All physical reality is calculated from them. The International System of Units, or the SI, defines these exact 7 base quantities. You've got length in meters, mass in kilograms, time in seconds, electric current in amperes, and so on. Every single other measurement in the universe is built entirely from these 7 foundational blocks. It's like a giant puzzle.
And the really cool part is, we can take those 7 basic pillars and mash them together mathematically to get what we call derived quantities. Just look at velocity, for example. That's simply a length measurement divided by a time measurement, which gives us meters per second. Or take force, which is mass multiplied by acceleration, giving us newtons. These derived units beautifully simplify how scientists communicate, so we aren't constantly writing out these massive, clunky strings of base units.
Moving right along, Section 2, decoding dimensional analysis, the math of reality. Okay, this is where things get really cool. This gives you what is essentially a physics superpower. Let's walk through this step by step. Let's take force, for example. Step 1, we already know force equals mass times acceleration. Step 2, in purely dimensional terms, mass is represented by a capital M. Acceleration is length divided by time squared, or LT to the negative 2. Step 3, we just multiply them together. So the fundamental dimension of force is simply mLT to the negative 2. Suddenly, these super complex physics formulas become highly manageable when you just break them down to their bare physical nature.
So the crucial takeaway here is that this dimensional analysis acts as a built-in spell checker for scientific reality. We use it to verify the absolute correctness of equations. Think about it. If the dimensions on the left side of your equal sign don't perfectly match the dimensions on the right side, you immediately know your math is wrong before you've even plugged in a single number. No way around it. It also lets us easily convert units and figure out relationships between completely unknown quantities. It's a real game changer.
Up next, Section 3, scalars versus vectors, adding direction.
Right, so now that we have our units sorted out, we have to draw a really sharp dividing line and add a whole new layer of complexity. Scalar quantities possess magnitude only. Think mass, time, or speed. If I have 5 kilograms and I add 3 kilograms, I get 8 kilograms. Just simple, everyday algebra. But vector quantities? They possess both magnitude and direction. We're talking about things like velocity, force, or displacement. Adding a directional arrow to the mix completely changes the rules of the math we have to use. You aren't just asking how much anymore, you're asking how much and exactly which way.
Take a look at these specific real-world examples categorized side by side here. On the left, under scalars, you've got things like volume, density, work, and energy. But look over on the right, under vectors, and things completely change. Impulse, gravitational field strength, magnetic flux density. These vectors are represented graphically using straight arrows. The length of the arrow gives you the magnitude, and the arrowhead tells us the precise direction.
All right, moving into Section 4, multiplying vector quantities, the math of angles.
So, adding vectors is one thing, but multiplying them? That requires some highly specialized tools. First up, we have the scalar product, which you might know as the dot product. The formula is vector A dot vector B equals the magnitude of A times the magnitude of B times the cosine of the angle between them. Now, what is truly fascinating here is that the result is a scalar. When vectors are multiplied this way, the directional elements effectively just cancel each other out. And this is exactly how we calculate the work done when a force acts over a distance at a specific angle.
Now contrast that immediately with the vector product, or the cross product. Vector A cross vector B equals A times B times the sine of the angle between them, all multiplied by what we call an n-hat unit vector. Using the right-hand rule, this mathematical operation actually creates a completely new third directional vector that points entirely perpendicular to the original two vectors. I know, it's wild math, but it is absolutely essential.
Let's ground these abstract formulas in reality for a second. Like, why does this actually matter? Well, these mathematical rules are exactly how scientists calculate vital physical phenomena in the real world. If you want to calculate power or figure out the projection of vectors, you have to use the dot product. But if you're trying to calculate rotational torque on an engine, map out angular momentum, or measure a magnetic force, you absolutely must use the cross product.
And our final section, number 5, the reality of measurement, the human element.
Up until now, we've basically lived in the realm of perfect mathematical models. But when we actually try to measure these things, the real world is messy. There is literally no such thing as a perfectly exact measurement. Everything contains some level of uncertainty. First, we have systematic errors. These produce consistent deviations in your data, usually because of poorly calibrated instruments or just bad experimental methods. A single systematic error, like a scale that always reads exactly 2 grams too heavy, can ruin an entire experiment. Though, hey, hopefully it just ruins your data and doesn't actually end up blowing up the lab, right? Then on the flip side, we have random errors. These vary unpredictably. They're often caused by observer estimation or tiny random fluctuations in the room's temperature.
Because of these errors, we really need to clarify an incredibly common point of confusion: accuracy versus precision. So accuracy refers to how close your measurement is to the absolute true value. Precision, however, refers to how close your repeated measurements are to one another. So it's entirely possible to have an instrument that is perfectly precise, giving you the exact same result every single time, but is wildly inaccurate because it has a systematic zero error.
And this brilliantly illustrates the human element in action. Notice how taking a reading from the wrong angle, which is what we call a parallax error, means your line of sight isn't perfectly perpendicular to the scale. Just moving your head slightly to the left or right generates an entirely avoidable random error in your measurement. So how do we track these human and mechanical mistakes mathematically? Well, we start with the first foundational error formula: absolute error. It's exactly what it sounds like. It is simply the absolute value of your measured value minus the true value. It just tells you the raw magnitude of how far off the mark your physical measurement actually was.
But here's the catch. Being off by 1 meter means very little on its own, right? Being off by 1 meter when you're measuring the distance to the moon? That is fantastic. But being off by 1 meter when you're building a kitchen table? That's a total disaster. And that is exactly why we calculate the relative error. By dividing the absolute error by the true value, we get a much clearer picture of the relative scale of our mistake.
Finally, to wrap up the math, we take that relative error and we multiply it by 100% to get our percentage error. This converts our relative fraction into a highly readable, standardized percentage. It's great because it allows scientists and engineers all over the world to immediately grasp just how reliable a given measurement truly is. Which brings us to the ultimate question of this whole explainer. Think about it. If no measurement is ever perfectly exact, and every single reading we ever take always contains some inherent physical uncertainty, well, how much of the universe's absolute truth can we ever truly measure? Are all of our scientific laws just incredibly precise approximations of a reality we can never perfectly touch? Think about that the next time you pick up a ruler. Thanks for joining me on this explainer. Keep questioning, keep measuring, and I'll catch you next time.